few reminders first. So there is one final homework. It's a single submission due on Wednesday. Because we don't have class on Friday and so on, when you submit the homework folder this time, if you've been keeping your old homeworks in there, just removing those and only putting the final submission homework in there, so that you don't have to worry about like, oh, I need to use those homeworks to revise. I mean, we'll obviously try to get them back to you as quickly as possible, but you don't want to be anxious while they're away. And we'll post the solutions to the homework, of course. Please check Moodle to see if there are any missing homework scores. We know about the missing quiz scores, don't worry, we'll take care of those. But yeah, if there are any missing homework scores, please let us know and yeah, help us fill in any missing spots in your grades. Yes? Oh, good point. There is still one tonight. I'll see about whether there can be a Wednesday night one as well. Yeah. Other questions? Okay. Did I take this out or put it in? No, should have kept better track. No, that's the dead one. Okay. All right. What else? Of course, the exam is on the 10th of May. Sorry, not 10th, 12th of May. Sorry about that. Some of you, because of travel issues, have it on the 10th. But for most of you, it's on the 12th of May. Yes. The exam will be cumulative, but about half of it will be on stuff after the second midterm, and then the other half will be on stuff, everything before the second midterm. But yes, it's all fair game. Electricity, magnetism, optics. Yes.
What time is the exam?
Oh, well, Emma first. Oh, okay. I believe it's 2 to 5, but I will double check on that. Thursday, 2 to 5. Yeah. Yes. Oh, a practice exam, you mean? I have to check with Dr. Bolt. Let's see what else. Yes, tomorrow, conceptual test and survey, 7:30 p.m. Yeah. Conceptual test, and then there'll be a survey, which will be, and you'll get an email from Dr. Edson about the survey after that. So that's separate from the conceptual test. But the conceptual test on Gauss's law, so please make sure to come for that. Yes, Louis.
Yeah, I just checked. It's Thursday 2 to 5.
Thursday 2 to 5. Thank you. All right, so that's the final exam. Thursday. 12. Yeah. Okay, I think those are all the reminders. Not picking up the mic for some reason. Okay, so geometric, oh, question, yes.
Conceptual test, like 7:30 to 9 is usually, it's like half an hour.
Exactly, yeah, you can come anytime between 7:30 and, well, I mean, don't come at 9 because then I don't want to, yeah. It should take about half an hour, 40 minutes at most, yeah. And this time you'll actually know what they're talking about when they say Gauss's law and flux and so on. So, yeah, better. All right. Any other questions? Yeah, I mean, everything we're covering now, yes. Yeah. We're not doing it. I mean, it is fun, but we're not doing it purely for fun. So, all right. We've been talking about light propagating in different media. We've talked about the idea of refractive index. We've talked about the law of refraction. So we have n1 sine theta 1 equals n2 sine theta 2. We have talked about total internal reflection. And yeah, and so that is, I mean, normally when you have light passing from one medium to another, there is some reflection and some refraction. But we saw that in certain cases there would be all reflection. Yeah, so let me see. I should put the screen down. Before I do that, yes, so there are some pretty cool simulations. So here you have the laser pointer and you can see, okay, it's going from one medium to another. You can see there's some reflection, some refraction. And you can move around and see how the angles change. You can change the medium or the index of refraction. And so here, all right, so let's say it's going from water into air, right? So this is water now, and this is air. Then you can see that, okay, there's reflection and refraction. But at some point, because we're going from a high refractive index to a low refractive index, what happens when the light ray switches media? It bends away from the normal because you're going to a lower end, so the angle has to increase. And so this angle is increasing faster than this angle does. So it will reach the horizontal first. And you see, oh, then we get total internal reflection and all of it just gets reflected. Okay. There's a cool phenomena which we won't study in this class, but if you go further in optics, you will, which is, so this is total internal reflection, and there is frustrated total internal reflection, where you can have, like, it's going from glass to air, and then you put another piece of glass just close by, but not touching. And then you get a sort of tunneling effect going on. Yes?
Just before the total internal reflection, will the reflected light be like intensity of it getting stronger and stronger?
Oh, I see. Yes, the intensity does get stronger and the refracted ray gets weaker as you get closer to that. I forget the exact expressions, but you can derive expressions for them. There is a systematic way that they behave. Yes?
Can you just turn on the wave version?
Oh, yeah,
I wanna
sure.
see what it looks like.
It's not terribly cool, but yeah, okay. Yeah. It does illustrate something interesting though. Right, so what are a couple of interesting things? So there is actually a weird but interesting way that you can derive the law of refraction, which is that supposing you have a light ray that goes from here to here. Let's say this is n equals 1, this is, say, n equals 1.5. And so it's going from point A to point B. And let's say that we want to find the path that takes the shortest time to go from A to B. And you know, it starts at A, ends at B. You want it to take the shortest time. So sort of first guess might be, oh, okay, let's just have it go in a straight line. But the problem with that is that we know it travels, so it should be a straight line. But yeah, anyhow, we know that it travels slower when it okay. We know that it travels slower when it's in this medium because of the refractive index. So you might say that, oh, we want to decrease the time. So instead, let's try and decrease how much of the path is in the second medium, because that will decrease how long it spends in the slow region. So in that case, you might say, oh, okay, maybe it goes like this. Oops. Okay, and so then that's a bit better. And what you can actually show is that you can play around with, okay, where do you put it, right? Because on the one hand, yes, this is less time in the slower medium, but on the other hand, it's a longer path, right? So you can play around with optimizing the time. And what's surprising is that you can show that what the final result, the one that optimizes it, is exactly the one that obeys the law of refraction. So yeah, you could say the light is seeking out the path which takes the least time. And so that was called Fermat's principle. He noticed that. And what's cool is that you can eventually sort of generalize that to mechanics. It's not time that it's trying to reduce, it's trying to reduce the quantity or extremize the quantity called action. And so that's where you get the phrase, the principle of least action. And that's why people talk about nature being lazy and so on, is it's trying to extremize action. Okay, question, yes.
So we have, I wasn't here physically, but there was a thing in the lecture that was the sine of the critical angle
Yes.
is equal to n2/n1 or
Right, yeah.
ratio. If the sine of that is greater, is it still the same? Oh, since the critical angle. But if it were to be like just the sine of, oh, okay, never mind, that makes sense.
Okay, good. Yes, Harry.
I wonder how would the light know which is the shortest?
Yeah. So yeah, it's you can get sort of lost in this, like, oh yeah, how does the light know? There are a couple of different answers to that. One is sort of, it leaks into quantum mechanics. The idea is that the light actually does take every possible path between A and B, but the ones that contribute the most are the ones which have this least time. Like they're all present, but they sort of interfere with each other, but the ones that interfere constructively are the ones that have that. Yes.
On the diagram, it shows a thinner portion going through the
Yes.
less. Why? What does that supposed to represent?
I think it's supposed to represent the intensity. No,
Because the
actually.
intensity looks like it's based off of how faded or how.
Oh, that's actually a good point. Yeah, no, that's right. That looks like it's off of the fade. Yep, you're right. It's the fadedness. I am not sure what the.
Yeah, that's what. Is it because it gets polarized?
I don't think so. But well, the wavelength should be related more to the spacing. I'm not sure. That's a good question. I will have to look into the documentation for this. It can't be the speed because that's changing as. And I don't think it's the wavelength, because I think the wavelength is represented by the spacing between the dark and light
And I don't think
bands.
it's related to intensity, because even as the thing gets fainter on the inside, it doesn't get thinner. What about frequency?
But then again, that shouldn't shift as I change the angle. Yeah. Cyrus, yeah.
I think it's just because if they made it the same thickness, it would sort of go off of the like the light coming in. Like it would be.
Oh, it would look, well, maybe. I don't know. I will look into the documentation on this simulation. But yeah, so yeah, so there's some cool stuff about light and how it propagates. What actually talking about polarization and wavefronts, when you're dealing with a plane wave, we've already seen that you have, say an electric field oscillating like this, and stuff like that. When we represent the wave with wavefronts, what we're doing basically is drawing a surface perpendicular to the direction of propagation, and usually through where the peak occurs. So what you're doing is drawing, these are called wavefronts. Wherever the peak occurs, and so then as the wave moves, these wavefronts move, and the spacing between them would be the wavelength lambda. And if you have a plane electromagnetic wave, then each of these wavefronts is an infinite plane, and so then they're all just, if they're moving this way, then they're all just moving like that. But you can have spherical wavefronts as well, in which case, the sphere is propagating outward in various directions. And at each point on a given wavefront, the electric field intensity would be the same. And for plane waves, not only the intensity, but the direction would also be the same. Yes?
How does the circular wavefront work with like the wave? Like where is the wave in that diagram?
Oh, I mean, you would have, depending on the polarization, you would have, well, basically sine waves, sort of
Going out
going
and all.
out and all. Though, actually, let me clarify. They wouldn't be perfect sine waves because the intensity will drop off as they go further away. But that same sort of oscillation, but with an overall decrease.
So it's a good way to represent unpolarized light,
What is?
the circular wavefronts.
No.
Because if it's unpolarized, it's going off in all directions.
No, I think you're confusing the direction of propagation with the direction of the electric field.
Oh, okay.
Because you can have a plane wave which is unpolarized as long as, like, the electric field is pointing in various directions. Yeah. Okay, so let's see. Anything else I wanted to say? Whoops. Wrong. Yeah, let's try some questions. So go ahead, grab your clickers. So let's see. Right, so we've talked about total internal reflection. So if you're in, say you're inside a swimming pool and looking out, or if you had a light source inside a swimming pool, you can see how after a certain angle it would bounce. And so get some interesting effects if you have lights inside a swimming pool. And we've talked about optic fibers and how they basically just bounce at extreme angles. All right, so here is my question to you. Show me your votes. E, all right, yes, E is correct. So just from the fact that we're looking for total internal reflection, we can immediately eliminate A, B, and C. because for total internal reflection, you have to be going from a large n to a smaller n, which isn't the case for A, B, and C. So we can eliminate those. So it comes down to D, E, and F. And we are looking for the largest critical angle. So we can say, okay, N1 sine theta critical is equal to N2 sine 90 degrees. Sine 90 is 1. So we get sine theta critical is N2 over N1. And so theta critical is inverse sine of N2 over N1. So we can see that, oh, when to get this as close to 90 as possible, these need to be as close as possible. And remember, what does it mean by saying it has a large theta critical? It means that you have to go to a very large angle before you see this total internal reflection. It's not easy to get total internal reflection, in other words. If the difference is large, right, if N2 is much smaller than N1, it means it's much easier to get total internal reflection. It happens at even a smaller angle.
What would happen if the critical angle was greater in that expression? Like a critical angle is greater than the angle of
The angle of incidence.
the angle of incidence is greater than the critical angle.
No, so that's when total internal reflection takes place. So the critical angle is when you have, so let's say this is the normal. So the critical angle is when you have light ray coming in, and then the outgoing ray is along the surface. Right? And then as soon as you go beyond theta critical, drawing it the wrong way. As soon as you go beyond theta critical, that's when you have total internal reflection.
So it just doesn't go out at all.
It doesn't refract at all.
Okay.
It totally reflects.
So do we throw that equation out the window when we get because there is no.
Yeah, because it doesn't make mathematical sense when you go beyond, because you end up if your angle here is greater than theta critical, then your sine of that angle will be smaller, and so then you end up with like, oh, sine of some angle is greater than 1, which doesn't make sense. Question? So always remember the angles in optics are measured relative to the normal, right? They're always measured relative to that perpendicular line at the point of incidence. Okay. I think before we move on to lenses and mirrors, let's see. Oh yes, so I've mentioned that different wavelengths, different colors of light actually have, for the same material, they'll have different refractive indices. And so typically what you see is this sort of relation. And you can sort of, this is just an empirical relation. You can sort of model it as n is equal to a plus b over lambda squared. A and b are just some constants. So you can see that as the wavelength increases, the n decreases. And so as a result, certain wavelengths of light would be bent more, certain wavelengths would be bent less. And this is what's behind the rainbow, because basically the light comes in all with all the wavelengths at the same angle, but then when it refracts, they refract at slightly different angles. And so you get that spreading and you get that spectrum or prism or rainbow effect. Okay, so there's that. And let's see what else. Yeah, let's get that for the moment. Yes, finally, just want to sort of mention, because we're doing physics, we're talking about optics. Let's talk about, at least briefly, why is the sky blue? So it turns out that the intensity. So when light travels through a medium, there's and like there's dust or air molecules or whatever, there's going to be some degree of scattering. And it turns out that certain, like the longer the wavelength, the less scattering there is. And that has an interesting effect. So red light has a longer wavelength than blue light, right? So the visible spectrum goes from roughly 400 nanometers to a little less than 700 nanometers. So red light is like 600, 660 nanometers. And blue light is, or violet is like 400 nanometers. This is the wavelength I'm talking about. So yeah, say 690 nanometers, red. So if you have a red laser pointer, it's usually in the like 630, 660 nanometer range. So red light has a longer wavelength, bluish light has a shorter wavelength. So when you are looking at the sun and it's directly overhead, what happens? The light that, the red light, which has a longer wavelength, will be what? Less scattered. Oh, yes, question.
So is the reason the sky is blue and not violet just because of lights, because it's more blue light?
It's a combination of the, yeah, the spectrum of the sun and like eyes sensitivity. Yes, that's right. So yeah, so what we see is that at midday, the light that is scattered is mostly blue, right? Because you have a shorter wavelength, that means you have more intensity at that wavelength. So at midday, you just see scattered blue light from all directions. The sky looks blue. When you're at sunset or sunrise, what happens is that the light rays are traveling through a much longer stretch of the atmosphere, right? And so the blue gets scattered in all various directions. The red light gets scattered less. And so that's sort of what survives to be seen by you at sunrise or sunset. Yes?
Doesn't it also have to do with the fact that when the sun rays come through the atmosphere, they're refracted at different rates, and so the blue is refracted the most?
Blue is refracted the most.
As the index of refraction of the greatest.
True, but I don't think the effect for air is that strong. So I don't think that's the major factor there. Yes.
I think he's also kind of talking about the absorbance spectrum of different chemical contents in the atmosphere, particularly that nitrogen is about 74% of the atmosphere.
True, but it's a clear colorless gas.
Well, it is, but cumulatively, it adds up. Is the point.
Not the leading factor. Certainly a factor, I won't deny it, but not the leading factor. Kyle.
Yeah, but then why is like the sky of Mars like red?
What was it that I read about that? It's partly to do with the dust in Mars, on Mars. I'll get back to you on that, but that's a good question. What's the question? Okay. Right. So this is not only about why the sky is blue, but it's also about why warning lights. One of the reasons why warning lights are usually red. Partly, of course, it's a psychological effect we have when we see red, and we associate with like blood and danger and whatnot.
In Wesleyan.
Also dangerous. But also because if you are looking at a warning light and it's foggy, right, which is usually when you would need the warning light most, the red light is dispersed by the fog least, and so is visible at greater distances through foggy conditions. Because the lambda would be largest, and so it won't be scattered as much, it will travel in straight lines towards you. All right. Okay, so moving on to lenses and mirrors. Yes, so we talked about ray diagrams already on Friday, got some practice with them. How do we deal with them quantitatively? We move to that board, just grab the eraser. So we've mentioned already there are converging and diverging lenses, and we said, oh, converging lenses are going to be thicker in the middle. And diverging ones would be thinner in the middle. And one way to sort of see why this makes sense is using that idea of, oh, the speed of light is slower in glass. So what happens when you have initially, so when you have parallel rays coming in, that corresponds to plane wavefronts, right? And what happens? They'll hit this part of the glass first, they'll start slowing down, right? This part over here is still traveling in the air a little bit, right? So it continues. And so eventually what by the time it exits the mirror over here, this part in the middle has been slowed down a lot. This part on the edges has traveled further. And so you end up with a wavefront that looks like this. And the rays are always perpendicular to the wavefront. So this is basically telling you that, oh, the light rays are going to start converging. So you end up with converging like that if you have more glass in the middle. In contrast, if you have plane wavefronts coming in over here, now the ones at the edges will be slowed down the most. The ones in the middle will be traveling further. And so once the wavefronts come out, they would be more like this. And so this corresponds to a diverging lens. Yes.
So those fisheye camera lenses.
Yes.
That like take in.
Like from extreme angles and yeah.
Are those made with converging lenses or diverging?
Those.
I'm talking more about like not so much what's being emitted through the lens, but like what's being taken in. You know what I mean?
Yeah, I think I know what you mean. I think those should be converging, but I'll have to double check. Because they would be able to get in angles at extreme and then sort of bring them in. Actually, no, let me think about that. Yeah, I'll get back to you on that. Yeah. Yes.
I think for that lens, this is kind of like the combination of both diverging and converging. So it's basically like you use the kind of lenses to like let more light in and then converge them.
And then
to
converge
your
it and
sensor.
form an image. Okay. That is probably what it is in the end. But yeah, I think in terms of getting in the extreme angles, it might be the divergent. But yeah, I don't want to speculate off the top of my head. I will check and get back. Okay, so converging, diverging. Let's see. Right. So for mirrors, there is a very nice simple equation governing where the image is formed if you have an object at some distance from the mirror. And okay, so this corresponds to the fact that this is what we were using before when we said that, oh, the focal point for a mirror is halfway between the center and the vertex. So that corresponds to the focal length being half the radius. So put it this way, for a mirror, we said this was the center, this was the vertex. So then this would be the radius, r, right? And then halfway between that will be the focal point. And so the focal length is the distance from the vertex to the focal point. R over here, focal point. So this would be the focal length denoted by small f. And yes, so we have this equation 1 over s plus 1 over s prime equals 1 over f. S here is the object to vertex distance. And S prime is basically vertex to image distance. Okay. And we'll do some problems next time that sort of go through the details of it. Let's see what else I would say. Okay, so we got F equals R over 2. We have this relation. What is cool and what would be helpful also for the homework is that it turns out thin lenses, the thin lens equation is the same. So amazingly, the same equation governs both spherical mirrors and thin lenses. All right, so since we only have a couple of minutes left, we'll end with some demos. Yeah, so one so it's this incandescent light bulb lens, and you can see the image on the blackboard, and if I focus it, you can see a pretty clear image of the coil, the incandescent coil of the light bulb. Okay. And you can see that if the distance isn't right, you get basically an unfocused image, whether you move too close or too far. Okay. And also so let's see if I can get the spacing right. Okay, yeah. So you can see a bunch of light rays, and then when they pass through this converging lens, they start to converge to the point. And of course, there are other shapes I could use. So if I just put a rectangular block, of course, nothing really changes, right? What is interesting though is if I put it at an angle, you get a shift, right? So this displaces it part. Question, or you just trying to visualize? Oh, block of this one. Yeah, sorry. There we go. And then let me actually darken the room a little bit, that will make it easier. There we go. Right, so you can see, and you can also see some reflection actually happening here. So there's some reflection, and then there's refraction, and then it comes out. So it goes air to glass to air. And so the exit angle is the same as ingoing angle, but it's being displaced because of the thickness of the slab. And here's that converging that I talked about before. And we have diverging as well, where you can see that it's now diverging stronger than and of course I could stick them together. In this case, they neutralize each other and you get very little effect. Last couple. Yeah. This is again, well, I mean, it's just a semicircle, but you can see what it's thicker in the middle, it's converging. You can sort of think of it as like, oh, the lens in your eye. Well, the lens in your eye is probably closer to this one. And we'll talk about eye defects next time. Finally. Right, so you can see flexion, fraction. Let's see if, yes, at the right angle, you get total internal reflection. And so it's coming, it's reflecting, doing total internal reflection of this coming out through that rays. See that if the angle isn't enough, then yes, it does pass through. But eventually, you see it's getting closer, closer to 90 degrees. Then, oh, in this case, it's actually coming back out this way. This is what they do in like periscopes and so on. Is like you have two mirrors or prisms that will do this. All right, that is it. Thank you.